Okay, guys, this is section 2.8 in the Stewart book. It's called the derivative as a function. The reason why I didn't really remember this section is because it's one of those hodgepodge kind of sections that, I mean, it has conceptual richness, but it's almost like, oh, by the way, here are a couple last few things that you need to know before you move on, okay? And they're all important, but they're all just sort of jammed into here. And you can probably sort of take it under three different headings. The first of which has to do with, okay, we'll just go ahead and, let's go ahead and talk about the takeaway. Okay, the takeaway from 2.8. And number one is the relationship between derivatives and continuity, okay? The next thing we need to talk about is how derivatives impact or affect, or, you know, they impact domain. And the third thing is the relationship between a function and its derivative, so f prime, and even f double prime. So basically, those are kind of the three takeaways that we need to talk about, and we'll just go ahead and we'll tackle those in order. Now, I don't know exactly how long this is going to take, because it's sort of, like I said, kind of like the last few things that you need to go before you move on. And so let's go ahead. Now, this is one of the big things that you need to know from 2.8. This is one of the theorems out of your book. It says if f is differentiable at a, then f is continuous at a. Okay? Now, that does not mean that if f is continuous, that it's differentiable. Okay, so be careful about the order. But basically, there are about three different ways in which that something is not differentiable. Okay, so a function can be not differentiable at a value of a if we have, you know, a jump discontinuity at a. If we have a jump discontinuity at a, okay, we know that there's no way to talk about the slope there, right? Because the slope is a comparison about what's happening to the left of it, what's happening immediately to the right of it, and therefore what's happening right at that point. And if there's no left or right, even though this function does exist up here, because I've actually colored that in to be inclusive, since the idea of slope has to do with the relationship that a particular point has with what is immediately ahead of it and what's immediately following it, if you're missing one of those components, it can't be differentiable at that point, okay? And therefore, since the limit doesn't exist here, the derivative doesn't exist here. And of course, the fact that it's not continuous tells us that there's a problem, okay? Now remember that there are also, there are also sort of, you know, like removable discontinuities. And it should make sense to us that if the function doesn't even exist here, that of course the derivative doesn't exist. And the last type of discontinuity that we need to speak of is, of course, the infinite discontinuity. Okay, we'll talk about that at A. And if the function doesn't even exist there, just like up in the removable discontinuity, then it's not differentiable. You can't talk meaningfully about the derivative, about the rate of change, or about the slope of the graph if you have something like this at A, right? If that is A, where the asymptote is, the function doesn't even exist there, okay? So obviously, discontinuity means that a function is not differentiable, meaning that if there's a discontinuity at A, the function's derivative is undefined at A, okay? Now, there are other ways in which something can be, like, a function can be not differentiable at a particular point. Okay, so if we have, let's say we have the function y is equal to the cube root of x. Okay, it looks something like that. Now notice that something strange happens right here at x is equal to 0. Okay, right at x is equal to 0, it goes, for a split second, it goes vertical. Okay, and therefore, because it goes vertical right there, and we know that a vertical slope is an undefined slope, we can say that that function is not differentiable at x is equal to 0. Okay, well, we've done this in terms of finding the derivative, right? And it was x to the 1/3, and then f prime. Does anybody happen to remember what it was? Well, it was 1/3 x to the 2/3, right? Well, it's obvious that this derivative, even though the function exists at 0, the derivative is undefined at 0 because the slope is undefined at 0 because it's vertical. Okay? Now another way, and this of course is basically roughly the same thing, if anything comes to what's called a cusp, or a sharp turn right here. Remember when we talked about, when I introduced the term back in Algebra 2 and Pre-Cal, we talked about differentiability, right, as a characteristic of polynomial graphs. Now I told you that that was going to be a concept that was introduced later, and for our purposes, okay, what that really meant about polynomial functions is that they were smooth curves, okay? And what I was trying to do was trying to differentiate it, pardon the pun, trying to show you that it was not something like this. It doesn't come to that point right there, okay? It doesn't come to a cusp. So there are several places in which a function can be not differentiable. It may be undifferentiable because it's discontinuous, but these are also two other ways in which a function can be non-differentiable at a particular point. Okay, but that actually is a very important theorem, because you'll be able to sort of deduce certain things when it comes to free response questions in May on the AP exam, but we'll of course come back to that before long. But I wanted to at least spend a few minutes explaining it and sort of fleshing it out, because it is mentioned in the chapter and it is relatively important. Now, in your book, you were assigned, okay, problems from that portion of the text, which is 21 to 31 on page 163. And she assigned you, let's see, she assigned you 23, and she assigned you 29. So I'm not going to do 23 and 29, but I am going to do 25 and 28, and we'll talk about how, because I mean the question states, find the derivative of the function using the definition of the derivative. Now state the domain of the function and the domain of its derivative. And what they're trying to get you to do here is they're trying to get you to discover by sort of discover in the doing, probably is a better way to put it, how the domain of the original function and the domain of the derivative relate to each other. And as we actually just saw from the y is equal to the cube root of x and its derivative, they're close. Because the only difference between the domain of this particular function, this is actually all reals, right? Negative infinity to infinity. The only difference here is that x cannot be equal to 0, right? So they agree at every single point except where the original has a vertical slope. Okay, so there is a relationship between the domains, and they're trying to get you to flesh this out. Now, we have talked, let's go ahead and do 25. Now, 25 is f of x is equal to x squared minus 2x cubed. Okay, now they want you to do that by the definition of the derivative. You can go ahead and toil away at that. I'm going to go ahead and let you know that f prime of x is 2x minus 6x squared. Now, I'm really more interested right now, since I've already done 4 separate videos on taking the derivative by limit definition, I'm more interested in the comparison of the domains. Now, what do we remember? First of all, definition of domain. Okay. Now, I hammered this into you for 2 years because I really want you to understand this. The domain is the set of all possible inputs. It is the set of all numbers that I can possibly plug into a particular function. Now, of course, the reason why I stated it that way and why I was so adamant that you remember the possible aspect of that, the possible in that definition, is because you need to be able to turn around and ask the question, okay, for what values is inputting into a particular function impossible? Are there any impossible inputs? And if you remember, when we talked about polynomial functions, the domain of polynomial functions is all reals. Okay, so the domain of a polynomial function is all reals. Well, here's the thing. A polynomial function will always have a derivative that is a polynomial function or a constant function. But I mean, basically, I mean, as long as you sort of group constant functions underneath the umbrella of polynomial functions, it basically fits. Anytime you have a polynomial function, its derivative will be a polynomial function. So the domain of both of these is negative infinity to infinity. Okay? Now, a little bit more difficult is 28. Okay, because they give you f of x is equal to x squared minus 1, 2x minus 3. Now, that is not fun. Okay? Now, in order to take the derivative of that particular function by definition, I would, and I strongly urge you to do this, I would go ahead and do the division. So if you do the division, it actually makes it a whole lot easier on yourself. Because once you do the division, and let's go ahead and do that on a separate sheet of paper. Let's see, 2x minus 3 into x squared plus 0x minus 1. Okay. How many times does 2x go into x squared? Well, it goes in 1/2 x times. I don't like the fraction, but whatever. Okay. And this winds up being x squared minus 3/2 x. And of course, you're subtracting this, so you get positive 3/2 x minus 1. How many times does 2 go into 3/2? Okay. So 2 is going into 3/2. How many times? Well, it goes in 3/4 of the time. Okay. Does that make sense? So we get 3/4, and that winds up being 3/2 x minus 9/4. And of course you're adding that, so it becomes 5/4. And so what we have here is this becomes 1/2 x plus 3/4 plus 5/4 over 2x minus 3. Now I guarantee that that's going to be a whole lot easier in order to take the derivative, okay? What you need to know in terms of the derivative is the fact that its f prime is equal to 1/2 minus, we'll go ahead and put the 5 up here and the 4 in the denominator right here, okay? Does that make sense? Okay. But what you actually wind up doing is that 4 actually becomes a 2, and you wind up with 2x minus 3 squared, okay? Now, what is the domain of this original function? X is not equal to 3/2. What is the domain of this function? Well, obviously you have the same restriction. It's the same asymptote. It just, you know, the factor happens to be squared instead of to the first power. So I'll explain, you know, this, how I got this will become apparent at a later date, okay? But what I want to show is the relationship between the domains. The original domain of f, okay, is exactly the same as f prime. the derivative will never exist where the original function doesn't exist. Okay? Because the derivative, for our purposes right now, and we can sort of flesh this out later, the derivative describes the behavior of the original function. So how can you describe the behavior of the original function at a point where the original function doesn't even exist? I mean, it just doesn't make any sense, okay? So you have to remember that any restriction on the original function in terms of domain, that restriction, at least that restriction, will show up in the derivative function, okay? And possibly more, like we saw with y is equal to x to the 1/3, right? The domain became more restricted as we took a derivative. Not much more, just at that one point, x is equal to 0, but it become more. It will never be more permissive as you take the derivative. It will always be more restricted because it is the derivative is describing the slope of the original function. Okay. Now I talked about this a little bit longer than I expected to. I'm going to go ahead and sort of end this video, and we will pick up the next one, and we will talk a little bit more about we'll talk about that third point right here, right? Okay. So going back to the takeaway. We've pretty much covered those two. Those have a lot to do with us just sort of talking a whole lot. This one right here has a lot to do with us playing with graphs, and we'll go ahead and do that here in the next video.